In this lecture, we're going to review the foundation for the resting membrane potential, and we'll conclude this lecture with a review of the first steps involved with the generation of the action potential. But when we talk about the resting membrane potential, we refer to that electrical charge separation between the outside of a cell, the extracellular fluid, and the cytosol, the intracellular environment when a cell is in a resting state. And so in a resting state, the neuron is not triggered to release a neurotransmitter that would allow it to communicate with another neuron or with a muscle cell. Likewise, a muscle cell at its resting membrane potential is not triggered to produce force. And so when we talk about the resting membrane potential value, the inside of the cell is more negative than the outside of the cell with respect to its electrical state. And so depending on the type of cell, the range of voltages are between negative 80 to negative 60 millivolts on the inside of the cell with respect to the outside of the cell. And we therefore say that the cell is in a polarized state, indicating negative on the inside, positive on the outside. And that's the difference between the aqueous medium inside the cell, the cytosol, versus the aqueous medium outside the cell, which is the extracellular fluid. And so the distribution of charged elements or ions inside and outside the cell, as well as negatively charged proteins on the inside of the cell, are responsible for that electrical state. If we take that polarized state of a resting cell and we do something to now depolarize the cell is no longer in that polarized state. And to do that, we need to add positive charges to this negative state inside the cell. And the way the cell does that is to introduce sodium, which is found in larger concentrations outside the cell. To repolarize a cell, the electrical state is restored back to the resting state, or what we call the polarized state. And that is done by the removal of positively charged elements when the cell has been depolarized. And so the action potential will step through a cell that is resting in a polarized state. The cell will then depolarize and will subsequently repolarize and will overshoot that repolarization and become hyperpolarized. And so when we look at the term hyperpolarized, we examine the polarized state. Numerically, it's somewhere between negative 80 and negative 60 depending upon the cell, and we just make it more negative or more polarized. And the two types of signals that we will focus on in the that are relevant to the resting membrane potential and the subsequent action potential are electrical signals and chemical signals, knowing that mechanical signals will also contribute to the action potential, but our focus will be on the relationship between electrical and chemical signals. To understand the resting membrane potential is to understand something called the Nernst equation. And the Nernst equation, as you see here in the middle of the slide, is a measure of what's called the equilibrium potential for a particular ion. So the equation is applied to one and only one ion at a time. And this equation is credited to the work of Walther Hurst, who won the Nobel Prize in 1920 as part of his work in thermochemistry, generated this equilibrium potential equation that takes into consideration a number of factors. And some of these factors include what's called the universal gas constant, and this is a value specific at a particular temperature. Of course, T stands for temperature in this regard, regarding the ion concentrations. The value of F is what's called Faraday's constant, and it's a value that is a set number put into the equation. And En is that equilibrium potential. So that's the voltage difference necessary to hold an ion in a particular concentration outside the cell and inside the cell. And when we calculate the Nernst potential, we only focus on one ion. So in the S symbol here represents a particular ion outside the cell, and the I and the 1 represents the concentration inside the cell. And so we'll work through an example here in calculating the Nernst potential for sodium. And so we have a slight reworking of the constant values here, but we'll use a constant value to substitute for this fraction. But we have the O, which indicates outside the cell. Using the square brackets, that indicates the sodium concentration in ionized form. I don't have the plus here, but in ionized form outside the cell, the concentration inside the cell. We take a constant value of 26.73 millivolts as we substitute for this fraction, and we'll use the values of 145 millimole of sodium outside the cell, and we have obviously less sodium inside the cell, and by substituting these values we can therefore calculate the Nernst potential. So now would be a good time to pause the video, go through the calculation, and restart the video. Okay, assuming you're restarting the video, we'll move on to the next slide, and we see if we work through the equation, we arrive at a Nernst potential for sodium, and we only concern ourselves with sodium, of positive 67 millivolts. What this value tells us is that in order to keep sodium in the concentrations outside the cell and inside the cell in a resting state, the electrical state inside the cell must be positive, a positive value of magnitude 67 millivolts. If we work through the same equation for potassium, we find a different Nernst value of negative 98 millivolts. And so really, what do these values mean? And so to hold sodium in its equilibrium concentrations, and these are the concentrations under a resting state, 145 millimole concentration outside, much less inside, we need a voltage difference of positive 67 on the inside of the cell. And the key concept here to bring further understanding to the Nernst equilibrium is that opposite charges attract, positive and negative attract, and like charges will repel. And so when we talk about positive or negative, we are referring to the polarity or the polar state of a particular molecule, an environment, or an ion. And so we first ask the question, what is the effect of a positive voltage inside the cell on sodium? Recall, we have more sodium outside, much less sodium inside, and if we have a positive voltage inside the cell, that will have a tendency to repel sodium. And because we have so much more sodium outside, that positive voltage inside the cell will contribute to keeping sodium outside the cell. The next question here is, what is the effect of a negative voltage on the inside of the cell for potassium? So if we go back up and we work our calculations and we calculated the Nernst potential for potassium of negative 98, that negative voltage would have a tendency of attracting the positively charged potassium ion. And so potassium would have a tendency of remaining inside the cell. So we know that the resting membrane potentials of cells are neither positive 67 nor negative 98, but this is what is necessary to hold sodium and potassium individually in their respective resting concentrations. Now, in order to determine what actually exists for a muscle cell, we have to take into consideration all of the molecules and all of the ions that have a net electrical charge, as well as those concentrations. And so in the previous Nernst equation, we are examining an ideal situation electrically to what is necessary to hold the concentrations in equilibrium. What we're looking at here in this equation, sometimes referred to as the reversal potential of a given cell, we take into consideration the major elements that contribute to the resting membrane potential. And so a skeletal muscle cell is approximately negative 65 millivolts, and this is what's calculated as the reversal potential for a muscle cell. So that is called the zero current potential. Now, you notice that negative 65 is certainly not zero, but negative 65 is the energy difference across the membrane to create zero current, where current refers to the actual movement, where negative 65 millivolts refers to the energy that would cause the movement. So when we look at current, current is referring to the actual flow of charged elements. And the reversal potential is essentially the weighted average of all the ion effects, not just the permeability, but also the concentrations. And so the P aspect, the permeability of the cell to that ion, will also be a function in determining the resting state of that cell. And just some examples of permeability values, relative permeability values. We see here that the permeability of potassium to the permeability of sodium through a sodium channel is very, very low. Because of this very low value, this very low ratio indicates that the permeability value in this fraction is much, much higher than that for the permeability of potassium. So potassium does not have a tendency of going through a sodium channel. However, if we consider the permeability of protons to the permeability of sodium through the sodium channel, we see that these very small protons are much more permeable as a result of the size of the particle and the fact that the particle can easily interact with negative residues on the interior of the protein channel, making protons much more permeable through the sodium channel than sodium. If we examine a potassium channel, we see that the tendency of sodium to go through a potassium channel than potassium is very, very small. So the denominator in this fraction is much larger than that for sodium. And this is notable because sodium is a smaller ion and physically can fit through the potassium channel, but has a very low ability to migrate through the potassium channel. So in this slide, we're going to examine the cellular mechanisms involved with the first step of the action potential, which is the transmission of communication between an alpha motor neuron and a skeletal muscle cell. So what we're looking at here on the upper left-hand corner is something called an NACHR. N stands for nicotinic, and these are channels that have the ability to bind a chemical called nicotine, and such channels are just simply referred to as nicotinic. ACH refers to a neurotransmitter released by neurons at the junction where the neuron plugs into a muscle cell, and that is acetylcholine. So acetylcholine released by terminal axons of alpha motor neurons is the neurotransmitter that will bind to what we call the postsynaptic membrane. This is the membrane on the other side of the synapse, that small gap of extracellular fluid that is basically the cell membrane of the muscle. And what we see here is what's called a ligand-gated sodium channel within the vicinity of the terminal axon. And a single ligand-gated sodium channel has unique portions of the protein, which refers to a small sequence of amino acids referred to as residues that have the ability to form chemical bonds with the acetylcholine neurotransmitter released by the terminal axons. And so each NACHR, each nicotinic acetylcholine receptor, R for receptor, can bind to acetylcholine neurotransmitters. And when this happens, it causes a conformational change, which is a slight change in the shape of the sodium channel, and as such, the pore of the sodium channel opens up, and because sodium is held in higher concentrations outside the cell, in that very thin gap between the neuron and the muscle cell, sodium will flow down its concentration gradient. And recall, the interior of the cell, the cytosol, is a negatively charged environment. It's more negative than the outside. And as such, we not only have a downhill concentration gradient driving sodium into the cell, we also have the negative environment that provides an electrostatic attraction for the positively charged sodium to move to the interior of the cell. Close to the ligand-gated channel, just slightly distal to that area where the neuron plugs into the muscle cell, are other proteins very similar to the ligand-gated sodium channel. These are the voltage-gated sodium channel. So very similar in structure, except that there are no binding sites for the acetylcholine neurotransmitter. And as such, without that ligand-gated activation, we see the inside of the cell is negative, the outside of the cell is more positive, and the activation gate. So a theoretical gate will be in a closed situation. There's also what is referred to as an inactivation gate, and the inactivation gate is open. But nevertheless, the main element here is that the ability for sodium to flow from outside to the inside is not possible because the gate is closed. However, when the ligand-gated channel opens up because of acetylcholine, the sodium that rushes in will disperse within the cytoplasm. And as it disperses, one sodium ion will chemically interact with a voltage-gated sodium channel, and that interaction will actually unlock the gate. So the activation gate, which is closed, will now open in the presence of the sodium, which has been allowed to enter the cell because of the neurotransmitter. The opening of the gate will initiate not only the very fast movement of sodium to the interior of the cell, but will also activate the inactivation gate. And so the inactivation gate will start to move slowly and will move into the inactivated position. This situation here is what we refer to as being depolarized. And the activation gate is very fast and involves the weak binding of sodium through the channel into the interior of the muscle cell. And once that initiates the slow inactivation gate, the inactivation gate will now move into the open pore and will prevent any more movement of sodium. So the flow of sodium from outside to the inside of the cell is a very fast yet very transient activity. The channels open for an extremely brief period of time before it moves into the depolarized state. And once depolarized, we see here in very small print here, the cell which originally was negative is now positive, and the outside is more negative. And in the depolarized state, sodium channels are closed. And so when a cell is actually depolarized, the sodium ions have already rushed into the cell. And that is the cause for that depolarized state of the muscle cell. The latter stages of the action potential include repolarization and hyperpolarization, which occur sequentially after this depolarization event. So this ends this lecture on the first step of the action potential that we will continue in the next lecture.